Hello? Yes, I'm audible.
Yes, sir, you're audible.
Yes, sir.
Okay, okay, thank you. Just wait or 2-3 minutes, then we'll start. Pradeep, your question is about the Lagrangian and Eulerian description, right?
Yes, sir. Sir told us, but the lecture it was not very clear actually.
Okay. I have some document regarding today. I have note regarding that Eulerian and on Lagrangian, as well as I have some concept about the velocity in for fluid and acceleration for fluid, like the acceleration in case of fluid, even the flow is steady, then acceleration in case of fluid is not zero. So I have this type of document and concepts we'll discuss today, and some basic problems uh, regarding this week 6, that is the fluid kinematics. And I have some concept regarding the whatever or the fluid mechanics is going on in 2023. I think this time some questions are more or less on an average numerical type. So some concept today I will discuss, which will definitely help you for solving your assignment. Let us wait another 1 minute, then we'll start.
So,
Yes, Francis.
if the gate syllabus says only about the Bernoulli's equation, then do we need to follow these applications of the Bernoulli's equation like venturimeter, orifice meter, and notches?
Yes.
But only in the syllabus they only just say about the Bernoulli's equation. They haven't mentioned about the applications of the Bernoulli's equation. So, uh, does that include that?
Okay, you are telling the Bernoulli equation is about the application of the Bernoulli equation, like
Yes, sir.
yes. So you are telling something the whether the Bernoulli equation is enough for that type of problems or something required the another equation. You are telling like that, or what your question exact? Francis, can you
As
tell?
so, actually, when I read this year's gate syllabus of fluid mechanics, they just say about they are only mentioned the Bernoulli's equation. They haven't mentioned that there is a application for the Bernoulli's equation
No.
included.
In okay. I got. In gate actually, okay. You are talking about the gate examination. Okay. In case of gate examination, Bernoulli equation, application of Bernoulli equation, the question will ask in the gate examination from the your venturimeter, pitot tube, and if the tank case, like the pipe is connected with one pipe to another pipe, so this type of question you can expect in the gate examination. Parallel pipe concept and series pipe concept. So
Okay, so they don't need to mention specifically like IC engine like that. They just say Bernoulli's equation.
yeah,
That means
your branch is civil or mechanical?
actually I'm mechanical.
Okay, you are the mechanical guy. Okay. So in mechanical, I think because I have my background in the civil background, so that's why I know very well about the what type of question asked in the civil engineering background in the gate, but specifically from the fluid mechanics in gate examination. But I have solved the fluid mechanics question of mechanical previous year gate question from the mechanical background also. So you can expect similar type of question in your background also, but for you, as you the mechanical background, you need to solve the previous year question uh, from previous year gate questions. Then you can easily get what type of question asking in the gate examination in the mechanical, especially in the mechanical branch. So Francis, the conclusion is
Okay, sir.
that you follow the previous year gate questions.
Okay, sir.
It will be better for you. Okay, now we'll start. Welcome in the fluid mechanics live TA session, week 6. I will move ahead with the questions, then some concept I will also discuss. So my slide is visible to all of you. Please, anyone tell?
Yes, sir.
Okay, okay, thank you. Now the slide is moving.
Yes, I'm
Yes, sir.
moving.
Okay, okay, thank you. So the basically the fluid kinematics. The week 6 is about the fluid kinematics. There are 3 lectures in the week 6, Lagrangian and the Eulerian description. And second lecture is I have written L1 by mistake, but second lecture is the motion and deformation of the fluid element, that is the acceleration kind of thing, and here we discuss about the shear strain and shear rate also. The fluid kinematics, that is the problem solving session. So now moving on the next. So basically the fluid kinematics, in fluid kinematics basically we have the two approach. First one is the disc. The first approach is that, let me take the pen. The first approach, that is the first way, uh, describe the detail of flow pattern at every point xyz in fluid field, that is the differential approach. And second approach is what, working on a finite region, that is the control volume approach, making a balance of flow in versus flow out, flow in, that is the flow enter in the system, and flow out from the control volume, that is the here written, and determine the gross effect such as force and torque on the body or the total energy exchange. Basically what is written here, that is the first way is that, let's say this is the domain with the fluid flow in the pipe, or you can assume also the channel, no problem, but for sake of understanding I have taken here pipe. The first way is that describe the detailed flow pattern at every point. Basically this is the point, there are lots of point in the fluid flow domain, so at every point describe the flow pattern, what is happening. And second approach is what, take a specific reason, and what is telling, making the balance of flow. Balance of flow means what is the force, pressure force this side, pressure force this side, weight of the fluid, this type of balance we can make and derive the equations. So these are the two approach. Now moving on the first the question, then after I have some concept regarding that, so let's try to solve the first question. The question 1 is about the convective acceleration of fluid particle in the direction of x. So the four option is given, A, B, C, D. Which one is correct? Please write your answer in the comment box. as quickly, then I will discuss some concept regarding that. I have a very excited and interesting concept today. We'll discuss both. So please write your answer in the chat box for the question number 1. Okay, the option B is correct. Okay, okay, option B. Yes. Sharif, if you want to tell something, please write your comment also. Then we'll move ahead. In between, basically, in case of fluid mechanics, uh, fluid or any object may flow in the direction x y z, but here the question is the acceleration of the fluid particle and the particle concept and fluid molecule concept, fluid parcel concept I will discuss in the next slide. Just for make a rhythm, I have put it the two questions. And okay, option B is correct. Fine. As you know from the previous classes, the option B is correct. And for question number 2, or later we come on the question number 2. First we discuss the concepts. So basically, the subject called the kinematics concern the study of motion. In fluid dynamic, the fluid kinematic is the study of how fluid flow and how describe the fluid motion. That is, in case of the fluid dynamics, what we do how fluid flow and how to describe the fluid motion. Basically, let's example, I want to write here something. Let's fluid flow in the pipe. This is the flow. This is the fluid flow in the pipe. What is written here? How fluid flow and how to describe the fluid motion. Basically, for flowing fluid, we need to describe means here we need to write the fluid motion in terms of mathematics. Like you already know the acceleration, how we write the acceleration. As you see the in the previous question number 1, we can write this type of these things. So how to describe means here we write the equation for the fluid motion. Now from a fundamental point of view, there are two distinct way to describe motion. Please be patient. At the end of this lecture, you feel something, you feel some confidence regarding that. So this lecture is maybe boring because of the lots of theory, but after this theory, you can feel some confidence in the fluid kinematics. Please be patient. So two distinct way what I have discussed earlier. The first and most familiar method is the one, and you can take the screenshot also before sketching my pen, is the one you learn from your high school or the previous your physics concept to follow the path of individual object. Let's say the here car is, that is the moving car in this direction, that is the road. So what is written here? You learn to follow the path of individual object. Let's say this one is the object 1. For example, we have all seen in the physics experiment in which a ball on a pool table, you can see here, this is the pool table and these are the ball. So this is the discussing ball on a pool table or a puck on an air hockey table collide with another ball or puck with the another wall. Okay, so basically you can understand simply the one ball is collide with the another ball. So this is the line meaning. So what is the Newton's law are used to describe the motion of such objects? Basically, when the when Newton given the laws, the Newton gives the laws for such type of bodies. But in our case, here the fluid. Let's see ahead, and we can accurately predict where they go and how momentum and kinetic energy are exchanged from one object to another. Here the momentum and kinetic energy exchange means what? Let me explain. You know the momentum equation. What is momentum? Momentum is equal to mass into velocity. Mass into velocity. So one object, let's say 1 kg, and moving with the velocity 1 meter per second, and another is object, let's say here the weight is 2 kg and the moving with velocity, let's say 1.5 meter per second. The momentum of this object is what? 1 kg into 1, that is a 1 kg meter per second. And for this, what is the momentum? That is a 2 into 1.5, that is a 3 kg meter per second. This is the momentum. When the body collide with each other, what will happen? The velocity of body will decrease. Mass will be constant. Mass will be constant for both bodies. Mass will be constant always for both bodies, but velocity will be increase or maybe decrease. So as you know, the momentum is depend on both mass and velocity. When the velocity will increase, momentum will increase. So that is the mass exchange, that is the momentum exchange. Means one body when collide with the another body, the the first body try to reduce or increase the velocity of another body, means the first body transfer the energy to the second body. That means the momentum transfer concept is this. When you come in the fluid mechanics, or when you come in case of the river channel flow, what will happen? Let me explain little bit more. Let's say the river channel is flowing like that. This is the cross sectional point of view I have shown. Let's say there is a wet flow, water flow is like that. This is the more depth, and this you can say that is the flood plain. This width is the flood plain. What is happening? At the floodplain, velocity is less as compared to the velocity in the main channel. Velocity in the main channel. So what is happening at that section? At that section, momentum is transferred because this velocity, this fluid particle try to move, try to move, try to move the faster of try to slow in the main channel particle, or the main channel fluid particle try to fast the adjacent flood plane particle. So at that junction, what is happening? The momentum transfer is happening. So you can easily understand with this concept. So now let us move on the Please let me. Or please, are you guys able to understand? If anyone not, yes, please. Anyone tell yes if you are getting something. Hello, I'm audible.
Yes. Yes.
Yes,
Yes, sir.
so Pradeep, you are and Francis and all people, you are able to understand what I am telling. If yes, please write in the comment box.
Yeah, I think the velocity will decrease actually as the two particles will collide with each other.
Yes, maybe decrease or maybe increase. It's depend on the mass. Okay, maybe decrease or maybe decrease. We don't predict these things. If the velocity decrease or increase, here is the not meaning. Meaning is that if the velocity is decrease means what? The another the mass first or the first body try to decrease something, it means it resists. So that is the transfer of energy, maybe the resisting force body first transfer to the body second. So meaning is that here
Yes,
momentum
sir.
transfer will happen.
Yes.
So now moving ahead, what is so in the
So actually, you were
yes.
saying like the BF and BF floodplain and the it's actually having decreased velocity since the momentum from the water is transferred to the soil.
Yes, yes. Basically, Francis, here what I am telling, the momentum transfer means what? Momentum transfer means what? Velocity, momentum is depend on two things, mass and velocity. Mass will never change of anybody. So what will be changed? The velocity will be changed. So if the velocity decrease, the momentum decrease. If velocity increase, momentum. If one body try to reduce the velocity of anything, it means what? The first body try to reduce the momentum of the second body, or maybe the first body try to uh, try to increase the velocity of anything. What will the momentum of that second thing will increase. So this is the concept here, is that the momentum is depend on both mass and velocity. So let me move ahead. The kinematic of such experiment involve keeping track of position vector. That is the what is the position vector, you know already, and I will explain. Let me read the line. Position vector means what? Let's say the one object, let's say this is the pipe, and in the pipe the length is what? Let's say the 5 meter. So here maybe at this distance maybe 1 meter, and you can for 1 meter I am using the x vector, right? So basically here is that meaning. The position vector means where is the location of the particle. So this is the meaning of position vector, and the velocity vector and the velocity of what? This particle. So these two things in the kinematics we need to track. If you want to track a point, you need to track these two things. Where is the location? From which location to which location body will travel? And the velocity, of course, velocity, how much the speed, and not velocity, how much the velocity, that is the direction and speed both. So that is a figure 4.2 is describing that. Let's say the object A, B, C, and the location of object A is this, and the velocity is this. So similarly, for A, B, C. Now, when this method is applied to following fluid, we call it the Lagrangian description of the fluid motion after the Italian mathematics Joseph Louis Lagrange. So basically, this is the concept behind it. When we try to solve the fluid, try to solve, when I tell you the try to solve means what? when we try to the mathematical formulation of the fluid flow, the mathematical, when we try to solve the fluid flow problem, that is when we try to describe the fluid flow in terms of mathematics. If we track the one fluid particle, let's say this is the fluid particle, this is moving here, the same fluid particle, this is moving here. If we tracking like that and derive the equations, this is known as the Lagrangian description. There is several example based on that. If you want, please follow, just type in the Google what types of the equation derived based on the Lagrangian description. Lots of equations are there, and the steps also definitely will be there. So what is the Lagrangian analysis? Is analogous to the closed system. You know the what is the closed system, the identity of the fluid particle should not be changed. That means if one particle is here, then the similarly particle should be here, not the another particle. That is the meaning that you learned in the thermodynamics. Francis, you can understand because your background is mechanical, and namely we follow a mass of fixed identity, that is things. The Lagrangian description require us to track the position and velocity. Concentrate here, the track the position and velocity both of each individual fluid parcel. A fluid parcel, fluid particle, and fluid molecules. You can let me explain what is the. Let's say the one glass water. This is the glass. One glass water. In one glass water, many fluid molecules are there. By the combination of fluid molecules, one fluid particle, that is the group of fluid molecules. Let's say how many group of fluid molecules, we don't know actually, but for the mathematical expression we just assume that some group of fluid molecules form a fluid parcel or fluid packet or fluid particle. This is the same name. This group of fluid particle, we can tell the fluid particle, also we can tell the fluid packet, and also we can tell the fluid parcel. So here what is written, the Lagrangian description require us to track the position and velocity of each individual fluid parcel. Let me explain. In case of the pipe flow or the open channel flow, here the lots of fluid molecules and the group of fluid molecules make the lots of fluid parcel or fluid particle. That is the, this one is the one fluid particle, this is the two fluid particle, 3 4. For each fluid particle we follow, for each fluid particle we write the another mathematics equation. For this we write the mathematics equation, another mathematics equation. For this we write the another mathematics equation. That is the meaning of the Lagrangian, and this is very difficult in case of the fluid mechanics. So we shifted on the Eulerian approach. I will discuss in the later. So let me again uh, again read this. In the Lagrangian description require us to track the position and velocity of each individual fluid parcel, which we refer to as a fluid particle and take to be parcel of fixed identity. Fixed identity means this is the same particle. If this particle is moving here, the same particle should be we follow, not at not the another particle if shifted here, we cannot write the equation for that. So I think the Nike, you can understand what is the Lagrangian approach.
Yeah,
Yes,
clear,
please.
clear.
Yes.
Yeah,
So in case of Lagrangian approach, what we do, in let's say the in the river flow, your background is civil, Nike.
yes, sir. Yep.
Okay, let me explain in case of the river. In case of Lagrangian approach, what will happen? You take one fluid parcel, you consider one fluid parcel and track over the length, this approach, and write the equation for that, how this fluid particle, there is a millions of fluid parcel in the river, or fluid particle in the river, how single fluid particle behave. uh, that is the concept of the Eulerian, but this is not possible for in case of the fluid mechanics, because of the millions of fluid parcel is there and fluid particle is there. So what we do, we shifted on the another approach I will discuss. Let me read this. As you can imagine, this method, that is the Lagrangian method of this, you can take the screenshot. This method of describing the motion of much more difficult for the fluids than the billiards ball. What is the billiards ball? Means the previous one. These are the ball. These, the billiards ball is this. In case of billiards ball, we generally we can see how the ball is moving and we can identify the fluid parcel. But in case of fluid, we can identify the ball, where is which ball we targeting. But in case of fluid particle, it is a mixing kind of thing and you cannot track the fluid particle. But in case of solid object, you easily, so that's why in case of the solid we follow the Lagrangian, not Lagrangian, because it's easy to identify the object where the one object is moving. But in case of fluid, millions of the fluid particle and mixing another, and how we can identify. So this is the problem with the Lagrangian case. So first of all, we cannot easily define and identify, that is the what I am talking, this is the written here only, the fluid particle as they move around. And secondly, a fluid is a continuum. You know, the fluid is a continuum, that is the attached with each other. There is no gap between this fluid particle. The macroscopic point of view, as you see the microscopic, the in between the fluid molecules there is a lot, there is a gap. But the macroscopic point of view, that is the for deriving the mathematical equations, uh, we consider it the joined with each other. So the intersection between the fluid parcel are not as easy to describe as the intersection between the distinct object like the ball and air hockey pucks. So this is the meaning what I was telling. Furthermore, the fluid particle continually deform as they move in the flow. As you know, the fluid particle, let's say this is the fluid particle, what is happening with this particle, as it moving in the direction, the deformation will be happen. Let's say the length of this fluid particle is L, but when it move from this direction and reaching at that point, what will be the length of this fluid particle, may be the L plus something. So this is the happening with this fluid particle also. The single fluid particle as moving in any direction, it deform also. But in case of ball, you just, there is a lots of ball in this case, is move from one place to another place, there is no deformation. There is no deformation. If the length is here, the ball is 1 meter, at that place is the length is 1 meter. But in case of fluid, this is not happening. So the meaning of this here. uh, Now moving on next paragraph. From a microscopic point of view, the microscopic point of view, what is written? Macroscopic point of view, fluid is a continuum. But in case of the microscopic point of view, what is written? A fluid is composed of billions of molecules that are continuously banging means what? Banging means the collide, you can, or a strike, you can understand, the continuously strike into one another. The micro, if you see the fluid, the microscope, what you will see, the each fluid particle collide with each other. this fluid particle colliding this fluid particle collide this fluid molecules collide this. So this is the happening in case of the fluid. Now, but as the task of following even the subset of the molecules is quite difficult, even for our fastest and the largest computer. In case of the computer, you cannot follow the fluid particle using the computer also. Nevertheless, there are many practical applications. इसके बावजूद what is happening is this type of things happening with the fluid. Uh, Nevertheless, there is a lots of applications of the Lagrangian description, such as what is the application? You remember always sometimes someone asked to you what is the application of the Lagrangian description, such as the tracking of a passive scalars in a flow to model the contaminant transport. In contaminant transport case, we can use this, we can use and rarefied gas dynamic calculation and concerning risk reentry of a spaceship into the earth atmosphere and the development of flow visualization and measurement system based on the particle tracking. If you want to something design, uh, if you want to some design the device for the particle tracking, then you should follow the Lagrangian description. So here it is reading the some applications. Okay, so now this thing is kind of a more common method of describing the fluid flow is the Eulerian description. Now I will discuss about the Eulerian description. So more common method of describing the fluid flow is the Eulerian description of fluid motion, named after the Swiss mathematician Leonhard Euler. Leonhard Euler. In the Eulerian description of fluid flow, a finite volume called the flow domain or control volume is defined. Let's say in the pi flow case, what we do at the place of single particle or single fluid partial tracking, what we do a control volume. Let's say this is the control volume. This is the control volume. Description: a finite volume called flow domain. This is known as the flow domain. Control volume or finite volume is defined in case of the Eulerian. And what we do after the defining this control volume, what we do through which fluid flow in means fluid enter, and fluid flow out. Fluid flow out means that is the in, and fluid flow out. Okay, this is the control volume and fluid flow and fluid in and fluid out. Now instead of tracking the individual fluid particle, we defined a field variables. Okay, instead of tracking a individual fluid particle, what we was doing in the Lagrangian, what we do, we define the field variables. Field variables means what? These are the field variables means the pressure, velocity, acceleration. So these are the field variables. I will explain more about this. Let me read. The field variables function of space and times within the control volume. Inside the control volume, what we do, we define the pressure, how the pressure is varying with respect to x direction, y direction, z direction, and time also. How the velocity is varying in x direction, y direction, z direction, and time also. And how acceleration is varying in the x direction, y direction. Field variables means what? Field variable means what? Let's from the general concept view. Let's the playground. This is the playground, or you can say the field. So in the field variable means what? This direction is field. This direction is, if something going in this direction, that is the what is happening. This guy is moving in x direction as well as and y direction as well as. So this is the meaning here. The how velocity is varying in the x direction, y direction, and the z direction. For example, within the control volume, the field variables at a particular location at a particular time is the value of the variable for whichever the fluid particle happen to occupy the location at that time. So the meaning is that, okay, this meaning I will, some mathematical concept about this I have, so I will discuss. So this is a nothing telling. What is telling? Uh, the field variable at a particular location, that is the, let's say that the location is this, the field variable at a particular location at a particular time, let's say the time is t, at a particular time is the value of variable, is the value of variable for which fluid particle happens to occupy the location at that time. Okay, for example, the pressure field is a scalar field variable for a general unsteady three-dimensional. Unsteady means what? When the steady case, there is no time thing is here. But for unsteady, the three-dimensional fluid flow in the Cartesian coordinate, that is the p is equal to function of xyz, and the vector field, that is a vector field variable. Vector field variable means this velocity is, if the direction is change of anything, that is the velocity changes. Whether let's say the fluid is moving in this direction with the velocity 2 meter per second. If the fluid is moving in this direction and the magnitude is same, but the velocity is different because the direction is changed. Okay, so you can just see here there is a control volume, and one point is there, the one point is there, and you can just think about x, y, and z. So here is the x, y, and z is there. The x, y, z, and the pressure is defined here, the x, y, z, and the velocity vector, you know the velocity vector, the x, y, z, and a particular time. What is written in the above, that things only written here. And the acceleration field you can also write likewise. The acceleration is like that. So collectively, these and other field variable define the flow field. This, what is the flow field? In case of the flow field, the pressure is there, velocity is there, acceleration is there. So these are the things variable define the flow field. So the velocity field is expand in the Cartesian coordinate. Let's say that is the x direction, this is the x direction, and y direction, and this is the z direction, y direction and the x direction, and the unit vector is I, this direction is j, and this direction is k. So you know the velocity in case of the fluid mechanics, what is this? It is the function of x, y, z, and t, all. That is the x, basically the velocity in three directions. So u comma v and w written here, and for u, as you know, u is depend on the three direction x, y, z and one time, v similarly and w similarly. So this thing is written like that, that is the v vector is equal to what, u in the x direction, y direction, z direction and t, v I is written here, and v x y z and w x y z. Now moving on the next thing. Okay.
So flow
Yes.
flow field means the last one, v equal to in u and
Yes,
u
yes.
equal to v.
Flow field means is what? Flow field means is this. In flow field means is nothing. You can simply understand the flow domain. Flow domain means, let's say, the pi flow, and flow field means what? The in which field the flow is flowing. This is the flow is flowing. But for the mathematical calculation, what we do? We just assume the volume, and in this volume what types of variable is there, that is the pressure is there and the velocity is there, acceleration is there. So these things, combined these things define the flow field. So nothing, the flow field means in which field, in which domain and which location the flow is flowing, and these flowing is defined by what type of variables in the flow field, the pressure, velocity, acceleration, you know all. So this is the concept. Now moving this concept, and one example is there, and after that we'll move on the, I think battery is low.
So, sir, in Lagrangian, we consider only velocity. We don't consider acceleration, etc. In Lagrangian,
Yes, please.
in Lagrangian method,
Yes, yes.
you only consider velocity only. We
No,
don't
no, no,
consider
no. Everything, everything. Just
everything.
for, yes, yes, just for sake of understanding or describing, we consider the velocity. Because why we take the velocity as a mean? Because in velocity is associated with the other fluid flow parameters. You know, in case of acceleration, you see the acceleration is depend on the what? The velocity, and the lots of fluid parameters depend on only velocity. If the velocity is changed, the another fluid parameter changes. That's why we try to describe in case of the fluid mechanics based on the velocity, because as using the velocity, lots of parameters uh, we can calculate indirectly if you know the velocity. So that's why, but all the fluid particle, now all the flow variables can be used in case of the Lagrangian as well as the Eulerian both. Now moving on the next, please be patient. A similar expansion can be performed for the acceleration field. Okay, what you have seen here, the acceleration field. Now in the Eulerian description, all such field variable are defined at any locations, that is the this location, in a control volume. This is the control volume. Let's say the flow domain is the control volume, and at an instant of time, that is the at a particular time, what is written in the Eulerian description, all such field variables means velocity, pressure, acceleration, are defined at any locations, at a particular location. Let's say the x value is here, what x value, let's say 1, y value is 2 and the z value is 3. So at that location, just for example, I have put it here, the 1 2 3. So at that locations, in the control volume and particular instant of time, in Eulerian description, all such field variables are defined. We defined actually at that at the particular location and time. In the Eulerian description, we do not really care what happened to the individual fluid particle. So here is the concept. In the Eulerian description, we do not really care about what happened in the individual fluid particle, but in case of what, in case of the Eulerian, we care about this, what happened with the individual fluid particle. But in this case there is no. Rather, we are concerned with pressure, what is happening with pressure, what is happening with velocity, what is happening with acceleration in case of the Eulerian description. In case of Eulerian description, we care about only what is, how the pressure is changes from one location to another, how the velocity is changes, how acceleration is changes. We care about only in case of only for only these flow field parameters. So this is the written here very conceptually. In the Eulerian description, we do not really care what happened to individual fluid particle. Rather, we are concerned with the pressure, velocity and acceleration etc of whichever fluid particle happens to be at the location of interest at the time of interest. Okay, let's say that this fluid particle is moving in the direction at that point, that is at time is equal to t plus delta t, and the location is something different, x plus delta x. Delta x means something is moving ahead, and y plus delta y and z plus delta y, z plus delta z. So location at that location, what is the pressure and what is the velocity and what is the acceleration. So we are care about only that. That is the fluid parameters we care about in case of the Eulerian. Okay, the difference between these two descriptions is made clearly by imagine a person standing beside a river. Just for example, you can understand easily the Lagrangian and the Eulerian description. A difference between these two description is made clear by imagining a person is standing beside a river and measuring its properties, and measuring the property, what is the flow velocity and what is the pressure. In the Lagrangian approach, he threw a probe means a velocity measuring device, he threw a probe that moved downstream with the water. What will do the in the previous classes I have discussed about this example. The similar example is given here. I was taken the example from here only. So what the person will do, if person want to measure the something based on the Lagrangian concept, what will do, the person throw the this velocity measuring device in the river, and the velocity measuring device will move in the downstream with the fluid, and the measure the velocity, how the fluid is moving and how velocity of the fluid changing. So this is the concept about the Lagrangian. And in the Eulerian approach, he anchor the probe. He anchor means he fix the fluid measuring device at a fixed location in the fluid water. And while there are many occasions in the Lagrangian description. Okay, this is the concept behind the Lagrangian and Eulerian. While there are many occasions in the Lagrangian description is useful, the Eulerian description is often more convenient for the fluid mechanics applications. Furthermore, experimental measurement are generally more suited to the Eulerian description. Most of the experimental measurement based on the Eulerian description. Let's say what we do, if we want to measure something, we fix something at a particular location for measuring the velocity and measuring the pressure. And maybe the if you want to the measure the air. So what we do, fix the instrument and air in and air out, and we measure the where is the what is the velocity and what is the pressure of the air. So most of the cases, in the most of the practical cases, the Eulerian description we use. One example is given in the wind tunnel. In a wind tunnel, for example, velocity or pressure probes are usually placed at a fixed location in the flow, measuring velocity and the pressure. However, whereas the equation of motion in the Lagrangian description following individual fluid particle are well known, that is the Newton's second law. Basically, Newton's second law is when the Newton's second law is given for individual fluid particle, individual object how moving from one place to another place. But in case of fluid mechanics, individual fluid particle we are not going to track, because we are going to use the Eulerian approach. Lagrangian approach is not Lagrangian approach is very difficult to in case of the fluid mechanics. So we are going to use the Eulerian approach, and as you know, the Newton's second law is not given for the is given for the only one object is how moving from one place to another place. So directly the Newton's second law we cannot use in the Eulerian description. So what we use, a Reynolds transport theorem we use. By the using of Reynolds transport theorem, we describe the Eulerian, we describe the Newton, we use the Newton's second law for the Eulerian description. So now moving ahead, one equation, one question is there, a very easy question. If you want, take the screenshot.
So,
Yes,
by Lagrangian approach, we mean it will be a differential approach, and by Euler it will be integral approach.
yes, 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 yes.
Okay, sir.
So if you want, take the screenshot, please take the screenshot. This is a very basic question. The question is that let's say let me explain about the question. About some two-dimensional flow is there. Let's say in the pipe, what is given, one fluid particle is moving from one place to another place, and the equation is given like that. In the u direction 0.5, when someone try to understand what he get, the equation of x direction velocity is that, and the equation in the y direction 1.5 minus 0.8 y j. So this is the equation is there for the velocity in x direction and the y direction. And what is telling here, at the stagnant point, find out the stagnant point. Where will be the stagnant point in case of if the flow follow this type of equation? So for a stagnant point, as you know, the velocity is 0 at the stagnant point. So 0.5 plus 0.8x equal to 0, 0.15, not 0.1.5 minus 0.8 y is equal to 0, and from x you can calculate here the minus 0.625, and from y you can calculate here this. So at that point, at that location, your velocity of the fluid will be 0. So this is the question. Now the acceleration, now the concept is there. If you be patient, and by this you can easily understand the concept of the acceleration. So acceleration is what? As you should now the I think as you should recall from your study of thermodynamics and the fundamental of the conservation law, such as conservation of mass that and the first law of thermodynamics, are expressed for system or fixed identity, also called the closed system. These are things we know already. In cases where the analysis of control volume, also called the open system, is more convenient than the system analysis. Okay. Here what is telling, the control volume approach is more convenient to solve. It is necessary to rewrite these fundamental laws into the form of applicable to the control volume. Here what is written, Newton's second law is given for the individual tracking system. Based on the individual tracking system, that is the one, your car is at that place, what is the velocity if we distance moving from that, the friction is given like that, the friction of the road is this. So on that basis your Newton's law working only. But in case of control volume, your not working, your Newton's law will not work. So what we do for that, we need to the calculate, so we need to do the mathematical manipulation for applicability of the Newton's law. Here only written the same principle apply here. In fact, there is a direct analogy between the system versus the control volume in the thermodynamic and the Lagrangian versus Eulerian in the fluid dynamics. The equations of motion for fluid flow, such as Newton's second law, are written for the fluid particle, which also called a material particle. What is written here? Let me read again because it will be difficult for you. Fundamental law into the form of the application to the control volume. It is necessary to write. The same principle apply here. In fact, there is a direct analogy between the system versus control volume in case of thermodynamic and Lagrangian versus Eulerian description in the fluid dynamics. The equations of motion for fluid flow, such as Newton's law, are written for the fluid particle, which we known as the material particle. What we are telling, that is the same thing here. The Newton's law is written for the particle level. If we were to follow the particle of fluid as it move around the fluid, we would be employing the Lagrangian description and the equation of motion would be directly applicable. If we follow the Lagrangian approach, that is the one fluid tracking system, we can directly use the Newton's second law. It is written here only. Okay. Now what is written? For example, if we do define a particle's location in a space in terms of a material point vector. Okay. Well, basically this is the material point or fluid particle, you can say. The location of fluid particle is what? That is the xt, yt and zt. That is the position of given here. That is the position of particle in x at particular time, the position of particle in y at a particular time, and the position of particle in z direction at a particular time. However, some mathematical manipulation is then necessary to convert the equation of motion into the form of applicable the Eulerian equations. So consider, for example, Newton's second law applicable for our fluid particle. We are focusing on the one single particle, and we are going to apply the Newton's second law. The force is equal to mass into acceleration. What is written here? For a particle, the mass of the particle and the acceleration of the particle. Now moving the next. Where is the F particle is what? Is the net force acting on the fluid particle. Net force acting on the fluid particle means, let's say the fluid particle is here, and what is the force is acting on the fluid particle in the direction, the weight of the fluid particle. So net force on acting on the fluid particle. Now the mass of the fluid particle you know already, and the acceleration, and a particle is what is the its acceleration, how the fluid is moving from one place to another. And by definition, the acceleration is what, you know the already, the acceleration, if you want to, acceleration is what, the rate of change of velocity, that is the change in velocity with respect to time. You know already, the only things is the acceleration of particle means the change in velocity of the particle with respect to the time. However, at any instant of time, the velocity of the particle is the same. Okay. However, at any instant of time, at a particular time, the velocity of the particle is the same as the local value of velocity field at the location. Here it is written what? At a particular time, at an instant of time, if at an instant of time, the particle velocity will be equal to what? Will be equal to the velocity field, will be equal to the value of the velocity field at a particular time. That is, let's say the volume, control volume. Let me, this is the pipe flow, and here I am, this is the nothing, control volume. At a particular time, the velocity of field, that is the, this is the field, if you consider the field, the velocity of field and the velocity of particle will be same at a particular time. We are not going to tracking at a different time, at a particular time. And this is the make sense, at a particular time at a location. If considering the same location, your control volume is there, at same location your fluid particle is there, at a, at a exact time your particle velocity will be same, and the your field velocity will be same. This is the written here. Okay. Of the particle, since the fluid particle move, the fluid particle move with the fluid by definition. Okay, since the fluid particle move with the fluid. Okay, now in the other words, if you want to try to understand in the other words, the velocity of particle at a particular time, what will be the velocity of, here I want to write the velocity of particle at a particular time, the velocity of same, the velocity of field, that is the velocity of field, that is the x, y, and the time is same. Let's say that at a t is equal to 1, t is equal to 8 a.m, t is equal to 8 a.m. The same thing I am going to written t equal to 8 a.m. This will be the same, this will be the same. So this is the meaning here. What is written in the above line is this, the mathematically. To take the time into time derivative in equation 4-6, what is I have written the, this is the 4-6. We must therefore use the chain rule. Why chain rule? Because here you, at a particular time your velocity is depend on x direction, y direction, z direction, and the t direction. When you go for the derivative, that is the, here your velocity is not depend only the single direction. So that's why you need this chain rule or the partial derivative, partial differential concept. So what we do here, the acceleration of the particle, it will be the dv by dt, and at the same time it it will be also be the change in velocity in x direction, y direction, z direction at a particular time. So you can write these things, all you can write these things like that. The dv by dt, that is the your for the your single particle, and for flow field you can write this like that, delta v by delta t. This is the chain rule. So these concept, we chain rule concept we use for describing the. And similarly you can see here, for t this is expression is here, for x this expression is here, for y this expression is here, and for z this expression is here. So here what is the conclusion is that here in this slide, at same time, let's say the same pipe, at the time is equal to t, the particle is here, and your fluid, your control volume is here also. At the same time, the velocity of velocity in the control volume and the velocity of particle will be same. That's why the both things will be equal. Both things will be equal, and using the chain rule we can easily write the equation. Here something interesting for you. In the equation 4.7, del is a partial derivative operator and d is a total derivative operator. D is what? The total derivative operator, and this is also known as the material derivative. Later we will explain about this also. Consider the second term on the right hand side, equation 4.7. Since the acceleration is defined as the following a fluid particle, that is the Lagrangian description, the rate of change of particle's x position with respect to time is x particle by, in here nothing is written. What is written here? dx by dt, you know the velocity in the x direction as per the Lagrangian. The particle of the particle of the position of particle at a particular time, what is given? The change in position of particle at with the change of the time in if we tracking the single fluid particle, this is given the u. So similarly for this u is given, for this v, and for this w we will use the here written. Furthermore, at any instant in the time under consideration, the material position vector, that is the material position vector what? X, Y and Z. Material position vector means in a pipe, the in the pipe, I am taking the example for pipe. Why? Just for your simplicity. In the pipe, the X, the location is particle is where? X particle and the y particle, and you can say if the Cartesian coordinate is like that, the your fluid particle is here, the this one is x, this one is y, and in the three direction your z is here. So this is a nothing but x, y, z means you can at a some, maybe at that point or maybe at that point. This is only for so the dimensions for the distance from the origin of the fluid particle in the Lagrangian frame is equal to the position vector in the Eulerian frame. So here is the very important concept, how the one thing from Eulerian to Lagrangian is shifted. How the one thing from Lagrangian to Eulerian is shifted means from this to this, how this things is shifting. So what is written here? Furthermore, at any instant of time, at a particular time under consideration, the material position vector, that is the xyz of the particle of the fluid particle in the Lagrangian frame is equal to the position vector, that is the xyz in the Eulerian frame. So what is the your equation now is turns like that, that is the dt by dt is equal to 1, is like that. And finally, at any instant of time t, the acceleration field, that is the equation 4.3 must be equal to the acceleration of the fluid particle that happen to occupy the location. This line is written here only for the at a particular particle, they written here at a particular particle at a particular time, the your Eulerian and the Lagrangian velocity or the acceleration will be same. This is written here, must equal to the acceleration of the fluid particle that happen to occupy the location xyz at that time. Why? Because the fluid particle is by definition accelerating with the fluid flow. You know, because of the fluid particle is by definition accelerating with the fluid flow, hence we may replace a particle, that is the acceleration of the particle with this for a particular time. For a particular time, the particle, a particle is replaced by the vector x, y, z and t. And to transfer from Lagrangian to Eulerian frame of reference, this is the simple. So acceleration of the fluid particle expressed as a field variable. So you know already that this is the main equation of the acceleration, in case of fluid flow. So this is the derivation of your del v by del t plus v vector and v, and the del operator here is the gradient operator, or we can say the or say also the del operator. So as you multiply with the same thing will, as you multiply with this, the same equation will be come up. So in the x direction, your acceleration is this del u by del, you know, they're familiar with this, but the concept behind this I have explained already. One thing is here also, the first term of the right hand side of equation 4.9, that is the del v by del t, is called the local acceleration, that is this is known as the local acceleration, and the and is non-zero only unsteady flow. When the flow will be unsteady, this will be the zero, this will be not zero. And the second term, this is called known as the advective acceleration or sometimes the convective acceleration. So here is what important, this term can be non-zero even after the steady flow. This is the important, you know already, this is a very important case, important thing. Del u by, I want to write in the x direction acceleration, del v by del y, and w del u by, this is the u, del z. If your flow is steady, then what is happening, this thing will be zero, but this thing is not zero. So this is the beauty of the fluid mechanics. Even your flow is steady, then your acceleration will not be zero, but in case of solid, if something is moving steady, that is the no change in velocity, then what is happen, the acceleration will not be acceleration will zero in case of solid, but in case of fluid mechanics, if the flow is steady, then it's not meaning is that the acceleration of the fluid flow will be zero, because the convective term is always there, which is not related to time. So these are the concept, and you can take the screenshot this also. From example, one example is there, you can take a screenshot.
So,
Yes.
so in that differential form, do we actually write like the del operator before the vector? I mean, instead of del dot v, do we write like v dot del?
What you telling exactly, I'm not getting. Wait, just wait, I will explain. Okay. Yes,
So
Francis, what you telling?
we have a differential equation form, isn't it, using del operator?
Yes, you want to write the differential equation using del operator, right?
Yes, sir. So here it's actually written like v dot del vector.
Yes, v dot del operator.
Okay, this is I found in one book like v dot del vector, but in the previous slide it's actually like written like del dot v, isn't it?
This one, this one.
So in the Frankham White textbook, actually it's written like del dot v.
Yeah, you are telling about this equation, this
Yes,
thing,
sir.
this thing.
Yes, sir.
Okay,
Yes.
let me explain. No problem. Let me explain. So what is written here? Del v by del v by del t. This term is not having any problem, right? But let me write this. I want to write these things separately.
So I want to add like actually in the vector calculation max, actually it's right written like del dot v. The del vector is actually coming before the v vector. Del operator is actually coming before the vector.
Okay, you are telling like that.
Yes, sir.
Del dot v, right?
Yes, sir.
Not like that.
Not like here. But in another in the Frankenberg text, it's actually written like the same like here, but the definition is actually kind of when we are doing v dot del, then it will be u dou by dou x plus v dou by dou y, like that. Not we are not getting the gradient directly. If we write the del dot v, then we will get the gradient. If we write the write it like here, then we will be getting u into dou by dou I cap plus.
Yes, yes.
Yeah, so
Yes,
if,
this is right. This is clear because in vector, u means what? U I and Vj and Wk, right? When you multiply with this, and del means what? Del means is written here already, I day by dx, dou by dou x plus j dou by dou y and k dou by dou z. When you will multiply, what you will get? You will get the dou u by dou x plus, or you can
So
dou.
if you are applying the del operator on V, then we will get this gradient form. I mean, dou u by dou x plus dou y by dou x. It's actually clear for me, but what my doubt is why we are writing like dou dot del dot V. I mean, the operator is coming after the vector, isn't it? In that case, we are not getting the gradient. Instead, they are showing like we will be getting u into dou by dou y cap plus the u is actually outside of the gradient. I mean I cap, not inside the partial differential. And then they multiply the v vector, and then we will get the gradient along with it.
Okay, Francis, exactly I am not getting what you are telling, but for your sake of understanding, if you are multiplying with this, what you will get, del u by del x plus del u by, I
Yes,
think
sir.
I
This is the
will
same
be
thing I said.
cancel out, and v del y and w del y del z, and another v is also there, right? Another
Yes,
v
sir.
is,
This is the way in which it's written like that. The same thing. You have written the same thing that I said.
okay.
So if the del is before the v, then we will be getting the gradient instead of this,
No,
like dou.
actually, I'm not getting. Just when you multiply this thing, na, you get these things, and v vector is already this side, so you can multiply the v vector inside your, yeah, del v vector by del x plus v del v vector by del y, and plus w del v vector by del z. So this v vector will be multiply in this what we you will get, you will multiply. And if you want to, you are telling, if something is written like that, what will happen? So del by del x I plus del by del y j, so this will be like that. So this is not, so you are telling like that, in one book is written like that, right?
No, sir. In the Frank and White, it's actually written like the same that you have written here. I mean, v dot del is actually the same definition that you have given, like u into dou by dou x plus v into dou by dou y plus w into dou by dou z.
Yes.
Uh, but what my doubt is actually the del operator will be coming before the vector operator and v dot del dot to v. Then we will get a gradient and then we will multiply with v and we will get the same equation.
Okay, if you can get, then it's okay, no problem. Okay, I will see these things, okay, no problem. Now, yes, some material derivative concept is there also. So these things, today is a very very informative class. I have some example also, but before going on the example, I want discuss.
So can you go to the previous slide? Just a simple query I have.
Yes,
So according to this 4.8, that 4 by 8, that equation, the,
4 by 8, where is?
the 4 minus 8, yeah, 4.8 equation, just before this, just before, yeah, just before this, yeah, 4.8. So yes,
Yes.
that's here. So the why we actually will do this, there is like acceleration the function of x, y, z, and t time. So once we do only with respect to time, I think that is enough. Why we should do x, y, z direction again? The acceleration.
Okay, okay. Yes, yes, yes. No, that is the concept. In case of, if you are taking, let's say, the on a road track, on a road, your car is moving, your car is moving in the x direction. So for describing the velocity of the acceleration of this, what you will do, how much your car is moving in the particular direction, that is the how much velocity with respect to the time, how the changes with velocity with respect to time, this is the acceleration in case of solid thing you are tracking. But in case of fluid, your fluid is not behaving like that, only the straight path, only the straight path, your fluid particle is not behaving, your fluid particle is behaving little bit like that, little bit like that, means your fluid particle is reaching in x direction, y direction, z direction also, and with respect to time also, right? You are getting something.
Yes, yeah.
So yes, your fluid particle not behaving like that solid. Your solid is moving in a straight direction. But in case of fluid particle, this is not in the case, in practical case. So what we do, we track the particle in we track the we check the acceleration in the x direction, y direction, z direction also. So how velocity changes with respect to x, with respect to y, with respect to z. So this is the concept. In case of solid, this is not required, but in case of fluid mechanics, because your fluid nature is like that. If you see in the river, your fluid particle is how moving. I mean, something your fluid. If you but this thing you cannot visualize, but if you put some color dye, then you can easily visualize how your fluid moving in direction, x direction, y direction. It is necessary to calculate the velocity, because what here we are doing, here we are doing the, we are trying to write the mathematical equation of the fluid flow, how the fluid flow, how the fluid particle is flowing from one place to another place. We are trying to write in the mathematics, and based on that we will using the computational fluid dynamic concept, we can without going on the field and without conducting the experiment, we can easily track the how the fluid your, how fluid behaving in the river, also in case of pipe. Later on you will learn about this all things. So material derivative is nothing but the total derivative, that is the d by dt. D by dt is known as the material derivative in case of the, here written is d by dt in equation 49 is given as a special name, the material derivative. Okay, and it is material derivative, this is known as, but in fluid mechanics we, it is assigned a special notation. In fluid mechanics, a special notation for material derivative we use d by dt, capital D by capital dt, in order to emphasize that the formed by the following a fluid particle as it moved through the flow field. Okay, this is the another name also of the material derivative, total, and the particle, Lagrangian, Eulerian, and the substantial derivative. These all name are same. So this is the definition. And for acceleration, so using this you can use, if we put here the velocity at every place, the velocity will become, if you put pressure here, the every place the pressure will become. So this is the material derivative kind of thing. So the shear strain rate, the question is about the shear strain rate, verticity. So about this I have also some, let me, okay, shear strain rate. Okay, I want to uh, tell something important thing, the very, if these things will be clear, then a problem will be automatic, will be easy. Though in case of the fluid mechanics, there are four types of deformation. What types of the translation, this is the translation, a, and the rotation, this is the rotation kind of thing, and the linear strain, this is the linear strain, and the shear strain, this is the shear strain. So your fluid velocity, right, in terms of this, as we have seen the earlier. So what is your rotation kind of thing, that is the rotation omega, here we are going to represent with the omega. So your rotation in x direction, y direction, and z direction is given in this equation, as you have seen clearly. If you want to write your rotation in the z direction, that is, I have some figure for you, let me explain. If you write the rotation in the z direction, the equation will be the del v by del x, minus del u by del y. So what is the rotation for pictorial representation I want to show here. Here you can see the rotation kind of thing. If your xy plane is here, that is the x plane, that is the x plane or y plane, something you imagine your copy, just put it on the your table, and one you consider the x and one you consider the y, and vertically the z, vertically z is given, vertically z is given, that is the x, this is the y, and this is the z, vertically z is given. So your z direction verticity means what? And verticity and your rotation is almost related with each other. So here is the, this diagram is about the verticity, but you can understand about the rotation also. So your rotation kind of, this rotation is like that. If the z direction means something, your fluid particle is rotating in the, that is the center of rotating, the axis of center of rotating in the z direction. If you want to write your rotation in the x direction, then what will happen? Your fluid particle is rotate like that. As you see here, the one direction is given like that, that is the your fluid particle in xy direction. This is the x direction and this is the y direction. This is the x direction, y direction is given here, and rotation of axis is z. So this is the meaning of let me, yes, the z direction. This equation you can easily understand. If the equation x, then the plane will be what? If the equation will be s, the plane will be y and z. Your fluid particle plane what? The y and z. And if you want to write the rotation in the y axis, then you take the plane x and z. If you want to write the rotation in the z axis, your plane should be uh, this x and y. So you can, this is the concept. And your strain is what? As you know from the very your mechanics concept, the strain is what? That is the del u by del x, the velocity of x direction, change in velocity in the x direction, in the x direction strain, change in velocity in the y direction, change in velocity in the z direction. This is the x strain. And strain rate, if you want to know the shear strain, your shear strain is like that. The shear strain is the half of the what? The shear strain in the xy plane, the del u by del y, as you, the velocity in the u direction, but velocity in the u direction, that is the u, and the divided by the, in the del y, the velocity in y direction divided by the del x. So these things you observe always, and for the derivation you follow the book. So these are the concept, and verticity concept is also there. Your verticity is like that. Verticity is the curl of the velocity, and your rotation is what? The rotation is what? The curl of velocity. The rotation is curl of velocity, and verticity is what? The the rotation is half curl of the rotation is these things. And what is the verticity? Verticity is this. So what will happen? So from this the del, the curl of velocity is what? 2 omega, that is a 2 omega, the verticity. So your verticity is equal to the 2 times of rotation, 2 times of the rotation. This is the main, your verticity is equal to the 2 times of rotation. So and nothing here. Now we will solve the questions. The question is very easy from the very beginning. I want to go. Yes. Your second question is what? Your second question is for a two-dimensional fluid element in the xy plane. In the xy plane, as you remember always, in the xy plane is like that. That is the x. This is the y and z. Xy plane means the rotation component. The xy plane is given, the rotation component should be, the rotation axis should be in the z direction. So what will be the your answer? Your answer will be the omega z is equal to what? Half velocity in the y direction with respect to x, velocity in the x direction with respect to y. So this is the answer. So which one is the correct? This one is the correct. So option number B is correct for that. So using these approach, you try to solve the questions. The shear strain, you all know the shear strain. Shear strain, one is the strain and shear strain. Shear strain is what? Shear strain is similar things. The half of the change in the velocity, that is the x direct x direction, and the y direction. Only things is, if you compare with the rotation equations, only the plus in between. In the case of the rotation, here is the minus, and in case of a strain, shear strain, it is the play. The only plus things is here. So which option is correct? Del u by del x, del v by del x plus del u by del y. Option number C is correct for this. And verticity is what? Verticity is the two times of the rotation. You know the verticity is what? Verticity is the curl of the, that is the curl of the velocity. But your rotation is what? Half of the curl of the velocity. Half of the curl of the velocity. So at that place you can put the verticity things. So your verticity will be the equal to 2 times of omega. These things is given here. Now we move on the next. Which of the following factor affect the verticity? Your verticity for that, okay. Yes, here you can think the verticity of the fluid element cannot be changed ex except through the action of viscosity. The verticity of the fluid only change when your viscosity will be changed, or if there any effect of the viscosity. Non-uniform heating, that is the temperature gradient, except through the action of verticity or the temperature gradient. Simply if temperature is written, there is nothing meaning. The temperature gradient should be written clearly, or the other non-uniform phenomena. So what is written here? In the inside the boundary layer, your fluid is rotating, but outside the boundary layer, the fluid particle not rotating. It is given here. So we consider the irrotational things above the boundary layer, and inside the boundary layer the rotation things. So this is the here. So which of the following factors affect the verticity? Only the viscosity, not temperature. Temperature gradient will be affect. The study of fluid motion without considering the factor force causing the motion is known as what? Is the kinematics. Kinematics of the fluid flow. And here you can just I want answer of this question from your side. The question number 7. The approach of identifying or tracking the individual fluid particle by its position, the velocity, etc., describing a function of time is Eulerian, Lagrangian, static, and the none of the above. I want the answer from your side. Yes, please. Okay. Okay, okay.
So in the previous question about the vote city, is it actually both temperature and viscosity, or it's actually temperature gradient? We need to
Yes,
specify.
yes. The temperature gradient should be there. Temperature gradient means what? That, yes, yes, please.
Sir, actually, the viscosity is depending on the temperature, isn't it? So, uh, can we say both are dependent? I mean, when the temperature changes, the viscosity will be changing, isn't it?
Yes, definitely. The temperature changes means what? The temperature changes means the temperature gradient.
Okay. Okay,
The
sir.
the temperature gradient means what? The temperature gradient is nothing but the temperature changes, right?
Yes, sir.
Okay, simply temperature. This is a not appropriate term here written, so that is why.
Sir, and in the boundary layer, inside the boundary layer, there will be rotation. Outside the boundary layer, there won't be any rotation.
Yes,
Is
yes,
it?
yes, yes, yes. This is the concept.
Okay, sir.
Okay,
It's
because
due
we
to the
have.
change
And
in velocity gradient.
if someone want to take the okay, I will come for the screenshot in the last. So you can take the screenshot and go through the very proper way, then you can easily understand what is the fluid kinematics. Lots of thing is there in the fluid kinematics, but basic things, these are the basic things. You can take the screenshot, I will show in the last. So here is the fluid kinematics, and the question number 7 is given, uh, the ap- the approach of identifying or tracking the individual fluid particle. The tracking the individual fluid particle is the concept for what? The Lagrangian approach. Individual fluid particle is the Lagrangian approach. For the steady compressible flow, the continuity equation can be taken. The compressible flow is given here, as you all know, the compressible flow. And one thing is what? One thing is steady. So in case of compressible, there is the no constant of your density. So which equation will be applicable for this?
A, sir, A.
Option A is not correct because your density is not changing.
All right. Yeah, yeah.
Yes. So basically the continuity equation what telling the mass conservation. That is the mass in equal to the mass out. So mass is equal to what? Volume, that is the density is equal to mass by volume. So we can write the this equation, density into volume. So rho into volume is what? Area into area into length. But in case of fluid, what do we use? The mass flow rate. Mass flow rate, mass flow rate. So here is a time thing is there. So what will the rho 1 a1 and length by time is v1. And similarly the rho 2 a2 v2. If your fluid is compressible, then compressible means the density will be same for both. Let's say the section 1 and section 2, at both section your density will be same if the compressible, if the incompressible flow. Here is the compressible case. So what will your density will be not similar at both the sections. So that's why this equation is, so option C is correct. Here is the one, but uh, the option D is written like that, rho 1 a1 divided by v1, rho 2 a2 divided by v2. So this is not correct. So question number 9 is what written, the flow in which the velocity of fluid at a particular fixed point changes with time is known as what? The flow in which velocity of fluid at a fixed point particular fixed point changes with time. Let's say this is the pipe and we are tracking at a particular point. Let's say that this point, and we are tracking, and it changes with time. Let's say that at t is equal to t1, velocity was v was your 1 meter per second. At t is equal to t2, v was is equal to 3 meter per second. With time it changes. So which type of flow? Right, if you want to write your answer in the chat box, I want to see. This is a very basics. Okay, unsteady flow. Okay, Francis. Unsteady flow, yes, correct. Yes, yes. Okay. For question number 10, if you go, a velocity field is given by u is equal to minus 3x, v is equal to 2y, and w is equal to z. Is the flow a steady or an steady? What? Okay, steady, yes. Why steady? Because of there is no temporal term is given in the equation, so that's why it is the steady flow. Now, because there is no temporal term, there is no timing given here, so that's why your velocity is not changing with time. That's why this is the steady flow. This is yes option. No. And the velocity vector of the fluid flow is given like that. V is equal to, I think not visible to all of you, so that's why I want to write I minus 10 x square yj plus 2tk. This is the written. Find the velocity of fluid particle at 1 2 3. That is the x y z is given what 2 1 3, and time is what 1. So at that time you need to find out the velocity. So what you will do, u is equal to how much 4x cube, v is equal to how much minus 10 x square y, and z is equal to how much 2t. Calculating, put the value of x, that is the 2, put the value of y, xy already given, put the value of t already given, and you calculate the velocity like that. Velocity is the u square plus y v square plus z w square. This is the your final velocity. This is the your final velocity for this question. For the above problem, find the acceleration in the x direction. You can take the screenshot. Find the acceleration means ax is what you know already, del u by del x, only u, del u by del t actually first, and del u by del x u plus v del u by del y plus w del v by del u by del z. So for u already you know the u, that is a 4x cube. So this del u by del t, there is no t term is here, so this is the 0, this is the 0, and u already you know the 4x cube, and del u by del y when you will differentiate how much, the 4 3 are 12 and x square. For similarly you can calculate, this is a very differentiation kind of thing. And similarly for the question number 13, the material acceleration, you know already the material acceleration.
So somebody is asking something.
Who is asking? Let me check. Can you please show the 5 6 again? Yes, definitely, sure. Yes, please take the screenshot. Okay people, you can take the whatever I have discussed, the concept, and this I hope, I think Pradeep, your concept is clear regarding the Eilerian and the
Yes, yes, yeah, very much. Yes.
yes.
Thank you so much.
So you take the screenshot for all questions. For question 7 8 9 10.
Last side today, sir. Last side.
Yes, 11 12.
Yeah, yeah.
11 12. Now 13 14. And if you want to take the screenshot of the concepts, you can take from here. Yes, so other kinematic descriptions. because from here I have little bit gone the fast, and this is, you can take the screenshot for this also. You go through, these are the this concept, your concept will be definitely clear about the fluid kinematics. Take the screenshot, take the screenshot for this also.
No, the previous one, James.
Yes, yes, you can take the screenshot.
Sir, what is the name of book, sir?
Yes. Only simply
Sir,
sir was telling,
book
yes, yes,
which?
whatever the sir was preferring in the class, Single Simbala and FM White,
Yes,
that,
sir.
yeah, that book only I have followed, nothing other.
Sir, one question, one doubt, sir. Can I raise, sir?
Yes, yes, definitely, sure.
Sir, in recent, just one slide before you shown that, sir, suppose a particle is flowing in a surrounding it, let's say,
Yes,
having
yes,
some velocity. So velocity we can represent that in terms of velocity, u, v, and w in respective component. That is
yes,
a
yes,
basic thing. So,
yes, yes,
but is it, sir, when we differentiate with respect to u, x, y, z, we get the acceleration in respective direction. So it is compulsory, sir. Means mathematically we can be seen. If you differentiate any velocity, we will get the acceleration. But theoretically, is it compulsory, or is it essentially to have an acceleration when we define any velocity? Because
yes,
any
yes. Okay,
component.
okay. I got your. First, you take the screenshot, then I will take your question on the board. If someone, if you want to take a screenshot, okay. Basically, these are the genuine dot. Uh, okay, I will explain. You can take the screenshot of these questions also. Some flow visualization kind of thing is given here. Okay, from here is fine. So your question is about, in case of fluid mechanics, you don't know whether, because the fluid particle you cannot see where is moving. Fluid particle is going like
Yes,
that or is moving like that in the only one direction, or is moving like that or whatever. You cannot
yes, sir.
visualize. That's why, for better approach, for approach to the natural things, we need to define the acceleration with respect to time. That is the, with respect to time, if you want to the x direction, as well as with respect to the space, that is the distance also. For approaching the, that is the x, and this is the y, v and u, and this is the w, del u by del z. So yes, in case of the fluid mechanics, it is necessary to consider the all the directions as well as time, because it is because in case if you see in the river flow, the one fluid particle is not, basically the fluid particle, why we are considering the fluid particle, just for are the mathematical equations, just for the mathematical equation. There is no concept of the fluid particle in the
Yes, sir.
practical way. In practically there is no concept of the fluid particle, but for the mathematical formulation, if we are as a human being, we are try to understand the natural things, how the nature is happening, how the water flow in the river and the pipe, just we are try to understand. For that, we develop with our mind, with the scientists, the Lagrangian and the Eulerian, the Lagrange and the Euler. So these are the scientists try to understand the fluid flow behavior. So consider the, someone consider the fluid particle for the mathematical formulation. So these kind of things. So I hope you clear your doubt.
So on this number five, I think you should be A and B, sir. Not A, according to me, because temperature also gives rise to vorticity.
Yes, because temperature change should be here there. The term temperature is not okay. You are getting. Here if the temperature change is written, it's okay.
Okay, okay.
Simply temperature is written, there is no meaning. Maybe the constant, maybe the changes, so that's why. If temperature change is there, then you can clearly say option B, option C is correct, both A and B. So okay, thank you all. We'll meet again
So,
on the, yes,
so if it's okay, can you share your mail ID?
mail ID. Francis, you asking about the mail ID?
Yes, sir. If you,
Yes, I
you
want,
can share.
just I will write in the chat box. Okay, I have written. Yes, please. If you want, you can mail me. And one, I have also mail ID. Yes, please. If you have some doubt and if you want something, please mail me on that mail ID.
Thank you, sir.
Okay. So thank you all. We'll meet again in the next class. Okay.
Thank you, sir.
Okay. Bye bye. Well.